Hi guys, we are going to have a quick look at some ramp theory now. The little noise in the background is my cat who is sitting underneath the computer in a precarious situation, trying to knock it down. Anyways, as I said, we're going to have a quick recap of all of our ramps theory. So starting off, first of all, with our inclined plane, and remembering that the biggest thing we have to do with an inclined plane is to tilt our axis. So we're going to tilt our axis, our XY axis, in order to meet the same slope as our ramp. Okay? And I'm just going to pick an angle in here, something like that, and then we're going to put a box on the slope. Now, when we are analyzing this, the first thing to remember is when we tilt our axis, we do it so all of our forces, with the exception of gravity, are in the plane of X and Y. Okay, so we don't have to do X and Y components for every single force that is involved in a ramp question. Now, that means that we do have X and Y components for gravity because gravity will be straight down. And when I say straight down, clearly I mean at a wonky angle. There we go. Straight down. So you can see that it is cutting through our ramp at an angle. And the good part about this is that if we draw it straight down like this, then when we're solving for the components of that gravity, so just going to label that as force gravity. I'm going to bring it down here just so it's a little bit bigger. What we'll be doing is breaking that down in the plane of our y to give us a y component to our gravity, and also in the plane of our x, an x component to that gravity. Now you can see that we have created a right angle triangle here, and the interesting thing is this angle in here is going to be the same as this angle here. Okay, that's by basic geometry that we have that situation. What that means, however, is that unlike everything else, cos is always x and sine is always y, except gravity on a ramp. Okay? And this triangle describes y. So we have, for example, here, if this is our angle, this would be the same as our 25 degrees slope here. Then our x component is going to be the opposite side. So if this is our opposite side, we'll be using sine. And here between the angle and the right angle corner, that means that this is our adjacent. So we'll be using cos to find that component. Okay, so cos is always x, sine is always y, except force of gravity on a ramp where we flip them. Okay, and that means fg of x will be simply fg, and then x, we're flipping it now, sine theta, and we solve for fg using mg, sine theta. Okay, so if we give our object a mass, let's say 12 kilograms, pardon me, then we can plug that in with our angle. Oh, bad timing or bad spacing. Okay, that's too terrible even for Carrie. Let's move it over. 12 kilogram mass times 9.81 meters per second squared times sine of our angle 25 degrees, like that. And the direction of our x component, okay, the direction of our x will be downslope, which according to our convention is negative. Usually we put that on the negative 9.81. And we do our math. calculator interlude. And we get sine theta, it's going to be 49.75062, yada, 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 yada. Force, newtons, direction, down the slope. Okay? So that would be our FG of x. Now our FG of y, that's going to be this guy here. Where's the orange? This guy here. And again, according to convention, it's going to be down, so that should be negative as well. I'll do it over here. FG of y, again, is just FG, and y is always sine, but flip it for force of gravity on a slope. So we're going to go cos x this puppy, or cos theta, pardon me, cos theta. Expand that out. Force of gravity is always mg, cosine of our angle. Fill in our mass and our acceleration and our angle, like that. Okay, and again, as we've already discussed, this is the y component. Y is going down according to our convention, so we put a negative sign in there for direction, but again, that direction is up to us to determine. And then calculator moments, math happens, and we end up with my cheat sheet over there, 106.69055, yada 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 newtons, and the direction is down. So that is our FG of y. So there are two components of gravity on a slope that we can use now for any other calculations that we require. So if I write them up here in a bit of a givens list, I'll write theta of my angle. We've already used these, but now I'll organize retroactively. And I've got my force of gravity in the x dimension, 49.75062, yada 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 newtons, and my FG of y of 106.69055 newtons, yada yada yada. Those are rounded values, so when you're doing your own calculations, make sure you keep all of those values in your calculator. So that's just analyzing force of gravity sitting on a slope. Now every situation will be different. You have to do a free body diagram for each individual situation. What I'd like to do is take you through a couple of them. The first scenario I want to have a look at is the block or the mass sits at rest on the slope. Okay? So our mass is simply sitting there, nothing's happening. Very exciting day in physics land. So what do? Well, let's analyze the forces involved if it's simply sitting there. So I'm going to draw my free body diagram. Whoops. Let's draw that on a slope like we do for most ramps. Okay? And again, our little convention there showing what direction we're using as positive. Now, we've already got force of gravity on there, so I'm going to leave it as a nice dramatic purple. And again, you can either draw the one force of gravity, sort of that net vector, or you can draw your y component and your x component onto it. I'm going to draw the components. So my y component will be here. My x component will be here. Now I do have a surface, so opposite force of gravity in the y, I'm going to have exactly opposite force normal. These two vector lines should be the same length because our box is simply sitting there, and in the y dimension there's no movement at all. So that means we have a balance of forces in the y dimension. So these two again should be roughly the same length. Now, if I have a look at my x dimension now, I've got my box sitting on the slope and it's not moving. Why isn't it moving? Because the way I have it drawn so far, I have an unbalanced force in the x dimension. I have force of gravity pulling the box down the slope, but I've told you it's sitting at rest. So that means we must have another force on our free body diagram that's causing that. If it's simply sitting there, no one's pushing it, there's no ropes holding it on or anything else, then that means we have an equal length arrow, hopefully those look equal lengths to you, of friction. And if it's just sitting there, it's not moving, that means we have friction, and specifically the type is static. So our static friction is holding us onto the slope. So again, if it's not moving, these two in the x dimension must be perfectly balanced. Okay? At rest means acceleration is 0. Okay? So those two must be perfectly balanced. That means for our givens list, for scenario 1, acceleration equals 0. And we also know a ton of other things as well. Our force normal is equal but opposite to force gravity in the y. So I know force normal, force gravity in the y was negative down 106. So force normal is plus 106 newtons. I also know that if force gravity and force friction are in balance, then I know the value for force friction. And that is equal but opposite to the x component of gravity. So now it's upslope 49,750 yada 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 newtons. Cool, hey? Look at all that information we know simply from analyzing the forces involved. I could take this one step further. I could ask the question, what coefficient of static friction, little s, would keep the mass at rest? Well, it looks confusing. I'm going to have to erase that. Keep that in your minds, everyone. But if you look, we already know what force friction is. Force of friction, whatever type it is simply mu Fn. Mu is our coefficient this time of static friction. If I want to solve for that coefficient, I'm simply going to take my static friction force and divide it by force normal, like that. Now, force of static friction, I know is, I'm going to just move that up over here. Whoops, my mu got carried away there. 49.750, yada yada yada, use all those values, up the slope, and my normal force is the 106. Okay, and force normal, force friction are both up slope or up the positive y, so it's a straightforward division, and I get roughly 0.466 yada 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 newtons, or pardon me, no units for coefficient of friction. My newtons cancel out here and here, giving us our static friction coefficient. So obviously I'm not worrying about sig digs here, just want to show you so that when you're calculating at home you have a few extra decimal places to work with. But look at that, we found the coefficient of static friction that allows our block to stay at rest. Alright, on to scenario 2. Alright guys, we're gonna now try another ramp with the same angle. My cat is saying hello. There she goes. We're going to try another ramp with the same angle, but this time, instead of just sitting there and being allowed to be held up by static friction, we're going to apply a force to it. Okay? So we have our little dude pulling on a rope straight parallel, or in perfect parallel to our ramp situation. I've just shrunkified our givens list here on the left. Last time we solved for the coefficient of static friction. I'm giving you the coefficient of kinetic friction and also the applied force. So now what we're going to do is see what our acceleration is given an applied force and a coefficient of friction like that. All right. So first of all, making sure we put our axis on to indicate what directions are positive and negative. And we'll go ahead and do a free body diagram in that plane as well. So here's our FBD. I'm going to cheat and just use that one as well. And this time, as I say, we have our force applied straight up the slope. So that means it's going to be lying along that positive x-axis. Okay. We also have force normal. Opposite to that, the y component of gravity, just like last time. And down slope in a perfectly straight line. Pretend that is a perfectly straight line. I'll just make it thicker. We have our x component. Now the only thing I don't have on there is friction yet. I'm going to put friction in red. And what I want to point out is, first of all, when you're dealing with friction, you have to deal with what direction the motion of the object is traveling in. So in this particular case, our motion is this way. And so our friction will be counter that downslope. Again, we're going to be involving a situation with motion, and that means if we have motion, oh, that pink is hard to see on the screen. If we have motion, that means our friction will be kinetic in nature. So putting it onto our free body diagram, downslope, force of friction, little k for kinetic. Analyze your situation next. First of all, if we do have friction, which we do, I'm telling you we do. Also, I'm giving you a coefficient for kinetic friction, so that is sort of a double whammy there that you do need to involve it. So if I have friction, because the formula for friction is mu Fn, Fn is in the opposite dimension to motion, so normally we wouldn't need to worry about it, but because we have friction, we need that force normal. So we will start in the y dimension in order to determine force normal. Once we have force normal, then we can come back to our dimension of motion, which is the x. All right. You can hear a little Roblox in the background. So sum of forces in the y, first of all. Again, there's no acceleration in the y. We're only using it to find that force normal. Because there's no acceleration in the y, the box is not jumping up and down on the slope, then red pen of death gets to play, and we cross this off like that. So what forces are we dealing with in the y? Well, in the y, we have normal and FGY. So Fn plus FGY equals 0. Now we're isolating for force normal, so we're going to subtract over force of gravity. Like this. And now what we see is that force normal is simply going to be equal to the opposite direction of force gravity in the y, which makes sense if you look at your free body diagram. Force gravity in the y is down, force normal is up. So this value should be negative, this value should be positive. If you look, we calculated that in the last little section. So I've already put it in my givens list, but just a reminder, Fg of y, when you're solving for force gravity on a ramp, you use the opposite trig function. So reminder, we got this by using mg cos theta. Okay, mg cos theta. So I can go ahead and shove that in there. I'm just leaving that 0 in to show us that reversal of sign. And that is, in brackets now, force of gravity in the y is down, what is it, 6905 newtons. Like that. Okay? So I don't have them up here. I probably should have put them in my givens list, that both of these are down. So Fg of x is down the negative x, and Fg of y is down excuse me, the negative y. So if you were a plus minus person, then both of those values would be negative. or you can simply keep track of those directions just as we've done here, and then apply the negative in your calculation. But again, the important bit here is that those negative signs and directions just mathematically reverse. That is a plus sign. Doo-dee-doo-dee-doo. It's hard to write at the bottom of the screen. 106.69 yada 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 newtons. And this direction is positive, so you can leave it as positive, or you can write up. So either one of those is perfectly fine. Okay, so force normal is the same as force of gravity in the y. The only difference is that the direction is pointed upwards. All right, so that's all we needed the y dimension for. Now we have force normal. We can use that to calculate our friction in our calculation. All right, so let's have a look at the dimension of motion now. The dimension of motion is where we're going to find the acceleration of the object, and that is up the slope. Okay, so we're going to start off sum of forces in the x is equal to max. Red pen of death does not get to play because we are not crossing that out. In fact, that is what we're solving for. So let's have a look at our forces. Well, we know we've got friction, Fg of x, and we also have that force applied. Like that. Okay? So if we have a look, force applied will be upslope, that will be positive. Both of these will be negative. So it's really going to be the difference between those downwards forces and the upwards force that give us our net force here that will cause our mass to accelerate. Okay? So that's what we're looking at. Now if I look at my givens list, I have a value for force of gravity x. We calculated that earlier. Force applied is a given value in our list. The only thing we don't have is kinetic. So everything else is a number except for this guy here. So you can either do it all in one step in your calculation, or if you prefer, I know some of you prefer, you can just come over to the side and do your friction calculation, over here. Okay, so we'll do it this way because if you're comfortable putting it in, you're not going to have a problem doing it this way. But if you're not comfortable putting it in, then this is a little more straightforward. So again, we've got numbers here and here. We'll calculate one here off to the side. And we go ahead, look at our mu. And again, it's kinetic friction, so we're going to choose the coefficient for kinetic friction, which is 0.118. So 0.118. Again, remember, coefficients do not have units. Multiplied by force normal. We just calculated that puppy. And that is our 106.690 yada yada newtons. Now make sure you use all those decimals in your actual calculation though. Okay? Now, force normal is upwards, so it's going to be a positive value, but overall, the direction of your kinetic force will be downhill. And so it's up to you where you do it again, but by convention, we tend to put a negative sign in here by our coefficient just to describe that direction. And then we bust out our handy dandy calculators, and magic happens, i.e. I've got it written on another board, and we find out that it is 12.58948, and a bunch of other numbers, newtons. Again, it's friction down the slope, so it's going to be a negative value. Okay, so there's our friction. Everything else is a number. Let's just make sure our directions are listed on our free body diagram just to help us remember for our calculation. So friction is negative, force gravity in the x is negative, and force applied is uphill, so it is positive. All right. Now that we have that value, we can go ahead and plug in numbers into our equation. I'll start off with kinetic friction. That's my 12.589 newtons. And just putting it in brackets for clarity, and reminding myself that that is down, plus f2 of x calculated earlier, 49.750 yada 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 newtons, and again force of gravity in the x, down, plus force applied given to us in the question, 98.0 upslope or positive, so that goes next. Positive, and that's going to be equal to, go away data booklet, mass times acceleration. So you could divide over mass and do that in one step, but I'm going to give you an intermediate value for that. I do have to bust out the calculator. I didn't do that one earlier. So I'll grab my calculator and just do this. 12.58948522. That's a negative value, plus negative 49.750 yada yada yada, plus 98 newtons. And I should get 35.66 yada 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 newtons. And the difference there is a positive one. 98 is bigger than both of these together, so it should be positive, which it is. And that'll be equal to mass times acceleration. Now my next step would simply be to isolate for acceleration by dividing both sides by mass. And the joy of the whiteboard is that means these can cancel out and leave us with acceleration like that. The mass of the object is 12 kilograms, so I'm going to wipe that out. 12 kilograms, like that. So, saved in my calculator with all those digits, divide by 12 kilograms, gives me my acceleration. 2.971 yada 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 meters per second squared. And that's my acceleration. Okay, so for significant digits, we're looking at 3. So we would simply round this, and I'm just going to do it up top here. Acceleration, 2.97 meters per second squared. You can say positive or upslope in the direction of the motion. And then a red victory box. And we're done. That's it. So that is a tricky force applied, box sliding, friction involved, etc., etc. Pretty much as complicated as we could possibly get. Now, the only other thing I want to quickly show you, I'm not going to do the calculations, just show you how we would set it up, is what happens. Oh well, let's just get rid of everything. You can have a stare at the back of my just out of the shower hair there. So my question is, what happens if we have, again, an object on a slope at an angle of theta? We do have friction. Okay, so we do have friction on this slope. So friction, yes. We also have an applied force. But this time, we've got some dude with very long arms pushing the box downhill instead. Okay? So in this case, our force applied is downslope. So when we do our free body diagram for this, we would still do it the same angle, roughly. This time, force applied will be downslope. Well, what else is acting on this object? We still have normal force or contact force with the surface. We still have, opposite to that, the y component of gravity. We still have downslope as well. Let me just make that a little neater. Downslope as well. We also have Fg of x. So force of gravity in the x, like that. So if the little dude here, is pushing the box downhill, my question to you is, what direction is the friction going to be? The motion is in the x. The net force is downhill. We could calculate acceleration, all that kind of stuff as well. But this time, force applied and force gravity pushing the box downhill means that the friction, dramatic pause while you insert the answer here, is upslope. So again, whatever the motion is, friction will be opposite. So friction would be upslope in this case. Look at my beautiful straight lines. They're amazing. But what we really have to look at is those signs this time. Force normal is up. Force of gravity is down. The y is pretty much always the same. Force gravity in the x is down. This time force applied would have a negative sign, and this time force friction would have a positive sign. Okay, so based on the directions, based on your little sketch, then your free body diagram, keep track of those signs and then put them into your formula below. All right, hopefully that helps clear up a few questions about ramps. Anything else? Send me an email. Bye for now, guys.